Tonight, we're going to show you a place no human being had ever seen until just recently. And we're genuine 2025, a spacecraft built and flown by the European and American space agencies together, did something unprecedented in the history of our species. It climbed above the flat plane where all the planets orbit, turned its cameras downward, and photographed the south pole of the sun, the very bottom of our star, a region that, in all the centuries of astronomy, through every telescope and every space mission, no eye and no camera had ever seen. And what the spacecraft saw there was not what anyone would hope to find. It did not find order. It did not find the clean, tidy magnetic pole of the textbook drawings. It found chaos. The magnetic field at the bottom of our star was a churning mess, a jumbled patchwork of north and south polarities tangled together in the same place, a pole that was not really a pole at all. The spacecraft had caught the sun in the middle of one of the most violent things a star can do. It was photographing a star in the act of turning its own magnetic field inside out. Now, here is why this matters to you, and why the right word for it truly is terrifying. That chaotic region at the bottom of the sun is not just a curiosity. It is, in a very real sense, the control room of the sun's fury. The magnetic field at the poles is the seed of the sun's storm cycle, the hidden engine that decides how violently our star will erupt in the years ahead. And the sun's eruptions are not harmless. They are explosions with the power of billions of nuclear bombs, storms that have already set telegraph wires on fire, already blacked out millions of people in seconds, and already missed destroying our modern world by a margin of just 9 days. Everything about that danger, how strong the next round of storms will be, when the fury will peak, whether our power grids and satellites are safe, traces back to the poles. And the deeply uncomfortable truth is this. Even now, even after finally seeing the pole, we still cannot predict what the sun will do. We are living beside a star whose storm engine we have only just glimpsed for the first time, and what we glimpsed was turmoil. By the end of tonight, you're going to understand why the sun's poles were hidden from us for all of history, what the spacecraft actually saw down there, why that swirling magnetic chaos exists, and why the pole of the sun holds the key to the storms that could one day bring our civilization to its knees. This is the story of the most important place on the sun, the moment we finally saw it, and the unsettling truth it revealed. Before we get started, base video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To feel the full weight of what happened in the spring of 2025, you first have to absorb a fact that sounds almost impossible. Until that moment, no human being and no machine built by human beings had ever seen the poles of the sun. Not seen them badly, not seen them at a distance, never seen them at all. The top and bottom of the brightest object in our sky, the star that rules our lives, remained completely unobserved for the entire history of our species. The sun's poles were, quite literally, the last unseen places in our corner of the cosmos. Consider how strange that is. The sun is the most studied star in the universe, by an overwhelming margin. We have watched it continuously for decades with fleets of telescopes and spacecraft. We have mapped its surface in exquisite detail, tracked every dark its face, recorded thousands of its eruptions, and even flown a probe directly through its outer atmosphere. We have used the vibrations rippling across its surface to peer inside it, mapping its hidden interior the way doctors image a body. By any measure, humanity knows the sun intimately. And yet, through all of that, two regions of our star remained stubbornly, completely hidden. The very top and the very bottom, the poles. Scientists who study the sun for a living describe these regions with a phrase usually reserved for unexplored continents: terra incognita, unknown territory, a blank space on the map of our own star. And this was not a blank space anyone was comfortable with. Patch of solar real estate. They are among the most important regions of the entire star. The poles are wired directly into the sun's deepest rhythm, the great cycle of magnetic activity that governs its storms and eruptions. The magnetic field that gathers at the poles acts as a kind of seed for the sun's future behavior, and measuring it is one of the only ways we have to anticipate how fierce our star will become. In other words, the one region of the sun that we most needed to see, the region that holds the clues to the storms that threaten our world, was precisely the region we could never look at. For all of history, humanity has been trying to forecast the fury of a star while blind to its control room. That blindness ended in March of 2025, when a spacecraft finally rose high enough to look down on the sun's south pole and take its picture. It was a genuine first in the history of exploration, the filling in of the last great blank on the map of the solar system. But the story of that image, what it took to capture it, and what it revealed, is far stranger and far more consequential than a simple photograph. Because the pole the spacecraft saw was not the pole anyone had drawn in the diagrams. It was a region in magnetic upheaval, a snapshot of a star in the middle of a transformation that most people do not even know the sun undergoes. To understand what we saw, and why it matters so much, we have to start at the beginning, with the question of why, in an age when we have photographed black holes and landed robots on comets, the poles of our own sun remained invisible for so long. Let's begin with the puzzle of the hidden poles. How is it possible that the most observed object in the sky kept two entire regions completely out of our sight? The answer is not that we lacked good telescopes or that the poles are somehow shrouded or dark. The answer is stranger. The poles were hidden by geometry, by the shape of the solar system itself, and by where within that shape we are allowed to stand. Think about how we always see the sun. The Earth circles the sun once a year, and crucially, it circles around the sun's middle, around its equator. Our planet's orbit lies in line with the sun's waist, which means that from the Earth, we are always viewing the sun from the side, at the level of its equator, never from above or below. And from that side-on viewpoint, the sun's poles are always at the extreme upper and lower edges of the solar disk, seen at a hopeless grazing angle. Imagine trying to study the top of a person's head while being forced to stand at their eye level for your entire life. You could learn their face in perfect detail. You could describe every feature, but the top of their head would remain a mystery, glimpsed only as a foreshortened sliver at the edge of your view, its details smeared and distorted by the angle. That was humanity's exact situation with the sun. We knew its face intimately. Its poles were a sliver at the edge, never once seen properly. And this was not just a problem for observers on the Earth. It was a problem for virtually every spacecraft we ever launched. Because our spacecraft are launched from the Earth, they inherit the Earth's motion and tend to remain in the same flat plane in which the Earth orbits. Nearly the entire fleet of sun-watching observatories humanity has ever deployed has circled the sun in that same flat plane, at the level of the equator, sharing our side-on view. Better instruments, closer orbits, sharper cameras, none of it could solve the fundamental problem because the problem was not resolution. The problem was position. Every eye we ever pointed at the sun was standing in the same place, at the sun's waist level, and from that place, the poles simply cannot be seen. The blind spot was built into the architecture of our viewpoint. So for centuries, the polar regions of the sun accumulated an almost mythic status among solar scientists. They were the missing piece, the unseen territory, the regions every model had to guess at and no observation could check. Scientists filled the gap with theory and inference, sketching what the poles probably looked like based on physics and on the distorted glimpses available from the side. But an educated guess is not an observation, and everyone knew it. The maps of the poles were maps of an unvisited land, and the frustration was sharpened by a fact we will explore shortly, that these unvisited lands were suspected to be the very engine room of the sun's storm cycle, the region that decides the fury we experience downstream at the Earth. The most important real estate on the sun was the one place we could not go, or rather, the one place we could not see from, because to see the poles, humanity would have to do something extraordinarily difficult. It would have to break out of the flat plane of the solar system itself. And that flat plane, as we are about to discover, is a cage with very high walls. The flat plane that traps our view of the sun has a name. It is called the ecliptic, and it is one of the most fundamental features of our solar system. Understanding the ecliptic, and why escaping it is so brutally difficult, is the key to understanding why the sun's poles stayed hidden for all of history, and why the mission that finally saw them ranks among the great feats of spaceflight. Here is the picture. Our solar system is astonishingly flat. The sun sits at the center, and the planets, all of them, orbit around it in very nearly the same plane, like marbles rolling on the surface of an invisible tabletop. The Earth rolls along that tabletop. So do Venus and Mars and Jupiter and the rest. This flatness is a fossil of the solar system's birth. The sun and planets formed from a vast spinning cloud of gas and dust, and as that cloud collapsed, its spin flattened it into a disk, the way a ball of pizza dough flattens as it is spun. The planets condensed within that disk, and they have been orbiting in its plane ever since. The ecliptic is that ancient disk's ghost, the flat sheet in which almost everything in the solar system moves. And because the disk formed around the sun's spinning middle, the plane of the ecliptic lines up closely with the sun's equator. Everything orbits the sun around its waist. Now, here is why this flatness becomes a cage. When we launch a spacecraft from the Earth, that spacecraft begins its journey already moving with the Earth, sharing our planet's tremendous orbital speed within the ecliptic plane. To tilt the spacecraft's orbit out of that plane, to angle it upward so that it can climb above the sun's equator and look down on a pole, you must change the direction of that enormous motion. And changing the direction of something moving at tens of thousands of miles per hour requires a staggering amount of energy, far more than simply speeding up or slowing down within the plane. This is one of the counterintuitive cruelties of orbital mechanics. Leaving the tabletop is one of the most expensive maneuvers in all of spaceflight. It is genuinely easier in terms of raw effort to send a spacecraft to the outer planets than to lift one high above the plane of the solar system. The walls of the cage are made not of stone, but of momentum, and they are among the highest walls in space exploration. This is why, for the entire space age, our sun-watching mission stayed on the tabletop. It was not a failure of imagination. Scientists had dreamed for decades of a mission that would rise above the ecliptic and gaze down on the sun's poles. The problem was always the same. No rocket could simply muscle a spacecraft out of the plane to the angles required. The energy demanded was beyond anything we could reasonably launch. And so the dream waited, decade after decade, while the poles of the sun remained hidden behind their walls of geometry, and while scientists grew ever more certain that those hidden regions held answers they desperately needed. Because the urgency here was never just curiosity. The poles were not merely unseen. They were suspected of being the single most important place on the sun for answering the question that hangs over our technological civilization. How violent will our star become? To understand why the poles hold that answer, we need to look at what the poles actually do. And what they do is nothing less than set the rhythm of the sun's fury. Why were scientists so desperate to see the sun's poles? Not for the view. They needed to see the poles because of what the poles control. Because hidden in those unobserved regions at the top and bottom of our star is the mechanism that governs the sun's great cycle of violence, the rhythm of storms and eruptions that directly threatens the world we have built. The poles, in a very real sense, are the control room of the sun's fury. And to understand that, you need to understand the sun's most important rhythm. The sun is not equally dangerous at all times. Its activity rises and falls in a great cycle lasting roughly 11 years. During the quiet phase of this cycle, called solar minimum, the sun's face is nearly blank, its eruptions rare, its behavior calm. But as the cycle builds toward its peak, called solar maximum, the sun transforms. Dark sunspots multiply across its surface, each one a knot of intense magnetic energy. Flares erupt with increasing frequency, explosions carrying the energy of billions of nuclear bombs. Vast clouds of magnetized plasma, billions of tons at a time, are hurled out into space. At solar maximum, the sun is a storming, erupting, dangerous star, and the space around the Earth fills with its fury. Then the activity fades, the sun quiets, and the cycle begins again. This 11-year heartbeat is the master rhythm of our star, and it is driven by the sun's magnetic field, which builds, tangles, erupts, and then does something almost unbelievable. It flips. At every solar maximum, the sun's entire magnetic field reverses, north becoming south and south becoming north, before the cycle starts anew with the poles swapped. And here is where the poles come in. The magnetic field that gathers at the sun's poles during the quiet phase of the cycle is not a passive leftover. It is the seed of the next cycle. The polar field is the raw material that the sun's internal engine, its dynamo, will stretch and wind and amplify into the sunspots and storms of the following decade. And this gives the polar field an extraordinary property. Its strength, measured at solar minimum, is the single best predictor scientists have ever found for how violent the next cycle will be. A strong polar field foretells a fierce cycle ahead, crowded with sunspots and eruptions. A weak polar field foretells a milder one. If you want to know how dangerous the sun will be in the coming decade, the answer is written before anywhere else at the poles. The most valuable forecast in solar physics is stored at the top and bottom of the star. Now put the pieces together, and you can feel the decades of frustration. The poles hold the seed of the next cycle. The seed predicts the coming storms. The coming storms are the ones that can damage our satellites, black out our power grids, and endanger our astronauts. And the poles were the one region of the sun that no instrument had ever properly observed. Humanity was attempting to forecast the fury of its star by squinting at the forecast source edge-on, through a distorting angle, from inside the cage of the ecliptic. Every prediction of the solar cycle ever made was built on foreshortened, degraded glimpses of the very field that matters most. Scientists knew, with complete clarity, that until someone climbed out of the plane and looked down on the poles directly, our understanding of the sun's storm engine would rest on guesswork at its foundation. That is why the mission we are about to meet was conceived. Not to take a pretty picture of an unseen place, but to finally stand above the control room of the sun's fury and read its instruments for the first time. The mission that finally broke out of the cage is called Solar Orbiter, and it is one of the most ambitious spacecraft ever sent toward our star. It is a European-led mission, built and flown by the European Space Agency together with NASA, a partnership of the two agencies with NASA contributing to its launch and its instruments. And from its conception, Solar Orbiter was designed around the dream that had waited for generations. It would be the mission to climb above the plane of the solar system and look down upon the poles of the sun. Solar Orbiter launched at the start of this decade, in early 2020, rising from the Earth and beginning a journey unlike any sun-watching mission before it. Its task was double. It would fly close to the sun, closer than the innermost planet, to study our star at intimate range with a suite of powerful instruments. But its defining ambition lay in the shape of its orbit. Over the years of its mission, Solar Orbiter would progressively tilt that orbit, angling it further and further out of the ecliptic plane, climbing step by step above the level of the sun's equator, until it could gaze down upon the polar regions that no eye had ever seen. The spacecraft was built, in essence, to do the impossibly expensive thing, to leave the tabletop of the solar system. And since no rocket could simply hurl it out of the plane, the mission's designers turned to the most elegant trick in spaceflight. They would borrow the power of a planet. The trick is called a gravity assist, and Solar Orbiter's partner in it is Venus. Again and again, over the course of its mission, the spacecraft swings close past Venus, and with each carefully aimed flyby, it uses the planet's gravity to bend and reshape its own orbit. Each encounter is choreographed to tilt the spacecraft's path a little further out of the ecliptic, lifting its orbit to a steeper angle above the sun's equator. No fuel could ever accomplish this, but Venus, with its planetary mass, can nudge the spacecraft's trajectory in ways no engine could afford, and the mission harvests those nudges systematically, flyby after flyby, year after year. One of the mission's own scientists gave this strategy a name that has become famous: the Stairway to Heaven. Each Venus flyby is another stair, another few degrees of climb, lifting Solar Orbiter higher above the plane of the planets and closer to a true view of the poles. It is a slow ascent, measured in years, but it is an ascent no machine in history had ever made with eyes to see. And by the early months of 2025, the climb had reached its first great landmark. Solar Orbiter's orbit had tilted to roughly 17 degrees above the sun's equator, the steepest solar viewing angle ever achieved by a camera-carrying spacecraft. 17 degrees may sound modest, but it was enough to change everything. For the first time, the spacecraft's view of the sun's south pole was no longer a hopeless edge on sliver. It could genuinely look down, at an angle, onto the polar region itself, seeing terrain that had been hidden since the invention of the telescope. The cage of the ecliptic had finally been climbed, not smashed through with brute force, but ascended patiently, stair by stair, on the gravity of Venus. The spacecraft was in position. The last unseen place in the solar system was about to have its portrait taken, and for that portrait, Solar Orbiter carried a set of eyes unlike any that had ever been pointed at a star's pole. Reaching a vantage point above the sun's pole would mean nothing without the right instruments to exploit it. A pole is not a single thing to be photographed. It is a layered, complex environment, a place of magnetic fields, glowing plasma and flowing material, and each layer tells a different part of the story. So Solar Orbiter carries a suite of scientific instruments, and when it turned toward the South Pole, 3 of them in particular became humanity's first true eyes on that hidden land. Together, they were designed to answer 3 questions. What does the pole's magnetic field atmosphere look like? And how is its material moving? The first eye, and for our story the most important, is an instrument called the Polarimetric and Heliosysmic Imager, known as PHI. This is the magnetic mapmaker. PHI can measure the magnetic field across the sun's surface, determining not just its strength but its direction, its polarity at each point. It produces maps in which regions of one magnetic polarity and regions of the opposite polarity are distinguished, revealing the true magnetic anatomy of whatever it observes. Remember that everything important about the poles is magnetic. The seed of the next cycle is a magnetic field. The tidy pole of the textbook drawings is a magnetic idea. So PHI was the instrument that would deliver the verdict, the eye that would look down at the South Pole and reveal, for the first time in history, what the magnetic field of a solar pole actually looks like. Every assumption, every model, every guess made across decades of blindness was waiting to be checked against PHI's first polar map. The second eye is the Extreme Ultraviolet Imager, EUI, which photographs the sun in ultraviolet light. This is the atmosphere watcher. The sun's outer atmosphere, its corona, glows in ultraviolet wavelengths invisible to human eyes, and EUI captures that glow in fine detail, revealing the structure of the hot plasma above the surface, the loops and plumes and bright networks shaped by the magnetic field. Over the pole, EUI would show the architecture of the polar atmosphere, the imprints that the churning magnetic field below leaves in the layers above. And the third eye is an instrument called SPICE, which analyzes the light from the sun's atmosphere in a way that reveals temperature and motion. SPICE can distinguish the glow of plasma at different temperatures, and crucially, it can measure how that plasma is flowing, tracking the movement of material across and around the polar region. If PHI maps the pole's magnetic anatomy and EUI photographs its atmosphere, SPICE takes its pulse, measuring the currents of hot gas in motion. 3 eyes, 3 layers of the hidden pole. The magnetic field, the glowing atmosphere, the flowing plasma. Together, they would transform the pole from a blank space into a fully characterized landscape, observed simultaneously in its structure, its light, and its motion. No polar region of any star had ever been examined this way, because no instrument had ever been in position to do it. And as Solar Orbiter climbed its stairway through the early months of 2025, these instruments were prepared for the observation campaign that generations of solar scientists had imagined and none had lived to perform. But before we witness what those eyes saw, our story owes a debt to a forgotten pioneer. Because Solar Orbiter, remarkable as it is, was not the first spacecraft ever to travel over the sun's poles. Decades earlier, another machine made that journey. It flew over both poles of the sun twice, and it saw absolutely nothing. Its strange, blind voyage is one of the great overlooked stories of space exploration, and it explains exactly why the images of 2025 were still a genuine first. Here is a twist that surprises almost everyone who hears this story. Solar Orbiter was not the first spacecraft to reach the sun's poles. That distinction belongs to a mission launched a generation earlier, in 1990, a joint American and European spacecraft called Ulysses. Ulysses did what seemed impossible for its era. It escaped the ecliptic plane entirely and flew high over both poles of the sun, not once but repeatedly, over a mission lasting nearly 2 decades. And yet, in all those years, in all those polar passages, Ulysses never captured a single image of the poles it was flying over. It was a pioneer that traveled blind, a ghost that went first and could not tell us what the place looked like. The story of how Ulysses escaped the plane is a piece of spaceflight audacity worth savoring. Remember that climbing out of the ecliptic requires an almost impossible amount of energy. Venus, the partner solar orbiter uses, can only tilt in orbit gradually, a few degrees at a time. Ulysses needed something far more powerful, and there was only one object in the solar system strong enough: Jupiter. The mission flew Ulysses outward, away from the Sun, all the way to the giant planet, and used Jupiter's colossal gravity as a slingshot, whipping the spacecraft around and hurling it downward, out of the plane entirely, into a huge looping orbit that carried it under the Sun's south pole and over its north pole. Where Solar Orbiter climbs a stairway, Ulysses took a catapult. It was flung over the poles by the largest planet in the solar system, achieving in one titanic maneuver an out-of-plane orbit steeper than anything flown before or since. So why did this triumphant pioneer see nothing? Because Ulysses carried no cameras. Not one imaging instrument was aboard. This was a deliberate choice, made for reasons of weight, cost, and scientific priorities of its era. Ulysses was built to feel the polar environment, not to see it. Its instruments measured the solar wind streaming past the spacecraft, the magnetic fields threading the space it flew through, the particles striking its detectors. And with those senses, it made genuinely important discoveries about the wind and the fields above the poles, mapping the invisible environment of high solar latitudes for the first time. But of the poles themselves, the actual regions on the Sun below, it could show us nothing. Ulysses passed over the most coveted unseen territory in solar science, twice over each pole, holding no camera to point at it. It is one of the great poignant ironies of space exploration. We sent a spacecraft to the one place every solar scientist longed to see, and it went there blind. And so the poles kept their secret for another generation. Ulysses proved the journey was possible and sampled the environment, but the visual reality of the poles, their magnetic maps, their glowing atmosphere, their true face, remained as unknown as ever. The blank space on the chart of the Sun stayed blank. That is why the events of March 2025 carry the historic weight they do. Solar Orbiter was not merely repeating an old journey with better equipment. It was completing an unfinished one. Where the ghost had passed blind, the new mission would finally arrive with eyes. And in the middle of that march, as the spacecraft reached the high point of its climb, 17 degrees above the solar equator, its three eyes turned together toward the south pole of the Sun, toward Terra Incognita, and began to record what no one in the entire history of the human species had ever seen. What came back in those images is where this story truly begins. In the middle of March 2025, Solar Orbiter reached the summit of its first great climb. The spacecraft was riding 15 degrees below the level of the Sun's equator, on its way to its maximum viewing angle of 17 degrees, high enough at last for a genuine look down onto the south polar region of the Sun. On the 16th and 17th of March, the spacecraft carried out its first high-angle observation campaign. PHI mapped the magnetic field. EUI photographed the ultraviolet glow of the polar atmosphere. SPICE measured the temperatures and flows of the polar plasma. For the first time in the history of our species, the pole of the Sun was being observed, truly observed, from above. It is worth pausing inside this moment because moments like it are almost extinct. We live in an age where it can feel as though everything has been seen. Every coastline mapped, every planet photographed, every corner of the sky catalogued. Genuine firsts, places where no human eye or instrument has ever looked, have become vanishingly rare. And yet here was one, hiding in the most conspicuous location imaginable, at the bottom of the star that lights our everyday. The scientists waiting for this data were in a position almost no modern scientist experiences. They genuinely did not know what they were about to see. The lead scientist of the magnetic imaging instrument said exactly that, in words that capture the moment perfectly. They did not know what to expect from these first observations, he said, because the sun's poles were literally terra incognita, unknown land. The leading experts on the sun, the people who had spent careers modeling and theorizing about this exact region, were admitting openly that they were about to look at something for which they had predictions, but no knowledge. Think about the layers of effort compressed into those 2 days of observation. A dream first proposed generations ago. A pioneer spacecraft that made the journey blind 3 decades earlier. Years of solar orbiters' patient stairway, flyby after flyby of Venus, each one tilting the orbit a few degrees higher. The engineering of instruments that could map a star's magnetism from tens of millions of miles away. All of it converged on the 16th and 17th of March, on a spacecraft hanging below the plane of the planets, cameras angled upward and inward toward the underside of the sun, recording the first true portrait of a solar pole. The data was stored aboard and began its journey back across space to the Earth, where teams of scientists waited to process the images that would fill in the last blank on the map of the solar system. And when those images were processed, when the magnetic maps from Phi came into focus and the scientists finally looked upon the south pole of the sun, they found themselves staring at something that would make headlines around the world. Not a serene, orderly polar cap, not the clean magnetic anchor of the textbook drawings. The first thing humanity ever saw at the pole of its star was disorder. Deep, striking, unmistakable disorder. The magnetic map of the South Pole came back as a churning patchwork of contradiction, a region that seemed to be at war with its own identity. The scientists reached for a word that rarely appears in official mission announcements, and it is the word that carried this discovery into news reports across the planet. What they saw at the bottom of the sun, they said, was a mess. Let's look closely at what the images actually revealed, because the details are what make this discovery so striking. When the scientists examined Phi's magnetic map of the sun's south pole, they were looking at a kind of chart in which the two magnetic polarities are marked differently. Patches of one polarity and patches of the opposite polarity, the magnetic north and the magnetic south of the field, laid out across the polar region. On a simple, orderly pole, such a map would look clean and uniform, one polarity dominating the entire region, the way the south end of a bar magnet is purely south. What the map of the real pole showed instead was a chaotic quilt, patches of north polarity and patches of south polarity, scattered and tangled together, side by side, all across the polar region, both polarities everywhere at once. The official description from the mission was blunt, and it is worth quoting in spirit because of how unusual such language is in formal science announcements. The magnetic field at the sun's south pole, the team reported, is currently a mess. A mess. Not subtly complex, not mildly irregular. A jumbled, disordered mixture in the one place where our mental picture of the sun insists on tidiness. Think of what a pole means in everyday experience. A bar magnet has a clean north end and a clean south end. The Earth has a magnetic north and a magnetic south, orderly enough that a compass needle faithfully points along them. A pole, by its very definition, is supposed to be a place where one magnetic identity rules. And yet here was the south pole of our own star, finally seen after all of history, displaying no single identity at all. It was north and south simultaneously, a checkerboard of contradiction, a pole that, magnetically speaking, was not really a pole. The ultraviolet eyes added their own layers to the portrait. EUI's images revealed the glowing architecture of the polar atmosphere, the bright network of the sun's churning surface magnetism imprinted on the layers above, arcs of light tracing the polar plasma. Spice mapped the temperatures of the polar gas and began tracking its motions. Together, the instruments showed a polar region that was anything but a quiet, frozen cap. It was structured, dynamic, alive with magnetic activity from the surface upward. But it was the magnetic map, that startling patchwork of mixed polarities, that defined the discovery. The first true image of a solar pole showed a star whose bottom was in a state of open magnetic turmoil. Now, an important question should be forming in your mind, and it is exactly the right question to ask. Is this what the pole always looks like? Is the bottom of the sun permanently a chaotic mess? The answer is no, and the reason why is where this story deepens from a strange image into something far more consequential. The chaos in those images is not a permanent feature. It is a symptom. The spacecraft happened to photograph the pole at an extraordinary moment in the sun's life, in the midst of an event so dramatic that most people would find it hard to believe it happens at all. The mess at the South Pole is the visible evidence of a star in the middle of reversing its entire magnetic field. To understand what we really saw in March of 2025, you have to understand the flip. And the flip is one of the most astonishing things our sun does. Before we reveal the event behind the chaos, let's make sure the strangeness of what was observed has fully landed, because it is genuinely bizarre, and sitting with that strangeness is part of understanding it. The South Pole of the sun, at the moment humanity first saw it, did not have a single magnetic identity. It held both polarities at once, mixed together across the same region. Let's unpack how deeply weird that is and what it physically means on the surface of the star. Start with the familiar. Take an ordinary bar magnet. Its south end is south. All of it. Every part of that end of the magnet shares one magnetic identity, and the field flows out of the magnet in a smooth, orderly pattern because of that purity. This is our template for what a pole is, and for most of the solar cycle, the sun's poles fit the template reasonably well. During the sun's quiet years, each polar cap is dominated by a single polarity, a coherent magnetic cap, orderly enough that scientists speak of the sun's overall field as resembling a giant bar magnet, with a clean magnetic north at one end and a clean magnetic south at the other. That is the sun of the textbook diagram. One star, two tidy magnetic poles, a field flowing gracefully between them. Now hold that picture next to what Phi actually photographed. Across the South Polar region, the magnetic map showed fragments of both identities scattered together. Here a patch where the field emerges from the sun. Beside it, a patch where the field plunges back in. North polarity and south polarity, interleaved across the pole like the squares of a crazed checkerboard. Physically, this means the polar surface is a landscape of magnetic contradiction, field lines rising out of the star in one patch and diving back into it in the neighboring patch, the smooth global pattern shattered into local fragments. A compass carried across this region would be useless, swinging wildly as it passed from patch to patch. The pole, in any meaningful magnetic sense, had no direction. It was not north. It was not south. It was both, and therefore neither. A pole that is not a pole. And here is the detail that transforms this from strange to profound. This is not how the pole always looks, and the scientists knew it the moment they saw the images. A solar pole spends most of each cycle as a coherent, single polarity cap. The shattered, dual identity state captured in those first images occurs only during one brief and dramatic window in the sun's 11-year rhythm. There is exactly one time when a pole of the sun loses its identity, when the old polarity crumbles into fragments while a new one fights to establish itself. when north and south coexist in the same churning region. That time is the reversal, the flip, the moment arriving once per cycle at the height of solar maximum, when the entire magnetic field of our star turns itself inside out. Humanity's first ever look at a solar pole happened to catch the pole in the very act of dying and being reborn as its own opposite. We photographed a star mid-transformation, and to appreciate how remarkable and how unsettling that is, you need to see the flip itself in full. Here is a fact about our sun that most people have never heard, and that sounds too dramatic to be true. Roughly every 11 years, the sun's entire magnetic field flips upside down. The magnetic North Pole and the magnetic South Pole trade places. The whole vast magnetic structure of our star, the field that shapes its atmosphere, drives its storms, and stretches across the entire solar system, reverses its direction completely. And this is not a rare catastrophe or a hypothetical. It is the sun's routine. It has happened over and over for as long as our star has existed, and it is happening, right now, in the years surrounding this very moment. The chaos photographed at the South Pole is this flip, caught in the act. Let's walk through the rhythm of it. The flip is welded to the solar cycle we met earlier. During solar minimum, the quiet years, the sun's field is at its most orderly, the bar magnet configuration, each pole capped with a single clean polarity. As the cycle builds toward maximum, the sun's internal dynamo wins the field tighter and tighter. Sunspots erupt across the surface carrying knots of intense magnetism, and the orderly global field becomes increasingly stressed and tangled. Then, at the peak, at solar maximum, the reversal unfolds. The old polar caps are eroded and broken apart. Magnetic fragments of the new opposite polarity migrate toward the poles and battle for territory. For a stretch of time, each pole becomes exactly what Solar Orbiter photographed, a contested zone, littered with patches of both polarities, the old identity dying, the new one not yet crowned. And then, gradually, the new polarity wins. A fresh, unified cap of opposite polarity builds up at each pole, the global field settles into its reversed configuration, and the sun coasts down toward the next minimum, wearing its magnetism inside out. 11 years later, it does the whole thing again. Now consider the timing of Solar Orbiter's climb. The spacecraft reached its viewing angle in early 2025, with the sun at the height of its current cycle, in the very window when the reversal was underway. This timing was not an accident, and the mission scientists understood its value completely. Getting a view of the poles at this exact moment meant watching the most mysterious phase of the entire cycle, the changeover itself, from the one vantage point where it can actually be seen. The mess in the images is the flip. Every scattered patch of clashing polarity on that magnetic map is a piece of the old field dissolving or a piece of the new field arriving. Humanity's first portrait of a solar pole is a battlefield photograph, taken in the middle of the war. Let the scale of what that means settle in. The object in those images is a star, a sphere that could swallow 1,000,000 Earths, an inferno of plasma whose field reaches out beyond the farthest planets. And it is turning its own magnetism inside out, as we watch. The engine performing this reversal churns away beneath the surface, vast flows of conducting plasma winding, and rebuilding the field in a process powerful enough to reorganize the magnetic structure of the entire solar system, and yet so far beyond our reach that we can only read its progress in the shifting patches at the poles. There is something genuinely humbling, even chilling, in seeing it up close for the first time. Our star is not a steady lamp. It is a dynamo in perpetual upheaval, demolishing and rebuilding its own magnetic identity again and again forever. But now we owe you an honest reckoning. Because when those images came back, was the science community shocked? Did the chaos overturn our theories? The truthful answer contains a twist, and the twist matters, because it points to where the real fear in this story actually lives. Here is where we must be completely honest with you, because this channel deals in real science, and the truth here is more interesting than the myth. When the images of the messy South Pole reached the scientists, were they blindsided? Did the chaos shatter their theories? No, and it is important to say so plainly. The sophisticated models of the sun's magnetic cycle had actually predicted that, at solar maximum, in the middle of the flip, the poles should look like a tangled mess of mixed polarities. One of the mission's leading scientists said it directly. The models predicted a tangled mess of patches of north and south polarity all over the place, he explained, and that is exactly what we see. In other words, the observation did not overturn the deep theory. It confirmed it. The naive textbook picture of a permanently tidy pole was wrong, yes. But the experts were not expecting tidiness at this moment. They were expecting turmoil, and turmoil is what they found. So does that deflate the story? Does the confirmation make the discovery less significant or the situation less unsettling? Quite the opposite, and here is why. First, understand what confirmation means after decades of total blindness. Until March of 2025, every model of the solar poles, however sophisticated, was a prediction about a place no one had ever observed. Confirming that the models got the character of the flipping pole right transforms them from educated guesswork into tested science. And it means the strange picture we have painted tonight, the star that shreds and rebuilds its own magnetic identity every 11 years, is not a theory anymore. It is an observed fact. We have now seen with our own instruments that the pole of our star genuinely dissolves into magnetic chaos during the reversal. The mess is real. The flip is real. The battlefield is real. That is not a comfort. That is a verified glimpse into how violent the inner workings of our star truly are. And second, this is the pivot on which the whole night turns. The confirmation of the mess is not where the fear in this story lives. The genuinely unsettling truth lies one level deeper, in the question the models still cannot answer. Because while the theories correctly predicted that the flipping pole would look chaotic, they cannot predict the things that actually matter to us. They cannot tell us exactly when a reversal will complete. They cannot tell us how strong the next cycle will be. They cannot forecast the fury. The sun's cycles vary enormously, some fierce, some feeble, and their timing drifts and stretches. And to this day, after a century of effort, our predictions of the coming cycle remain rough, contested, and frequently wrong. The current cycle itself made the point emphatically, arriving far stronger than the official forecasts anticipated. We have confirmed the shape of the chaos. We still cannot predict the storm. Hold those two truths together, because together they are the honest heart of this story. We have now seen the control room of the sun's fury for the first time, and we found it in exactly the state of upheaval that theory anticipated. A star mid-flip, its pole a contested battlefield of polarities. And at the same time, the output of that control room, the strength and timing of the storms it will send at our world, remains beyond our power to forecast. We can finally see the engine. We still cannot read its gauges. That is the real reason the word terrifying belongs in this story. Not because the pole looks strange, but because of what the pole governs and how blind we remain to its intentions. So let us now follow the wiring out of that control room and trace exactly how the chaos at the bottom of the sun connects to the storms that can reach across 93 million miles and strike the world you live in. Let's now draw the line, clearly and carefully, from the chaotic pole in those images to the danger that hangs over our modern world, because the connection is not vague or poetic. It is a physical chain, running from the magnetic patches at the bottom of the sun, through the star's internal engine, to the eruptions that can cripple satellites and darken continents. When you understand this chain, you understand why solar scientists treat the poles with such urgency, and why a messy polar map is more than a curiosity. The pole is the beginning of the storm. Here is the chain, link by link. It begins with the polar field, the magnetic cap that assembles at each pole during the sun's quiet years. That polar field is the seed. When the new cycle begins, the sun's internal dynamo, the vast machinery of flowing plasma beneath the surface, takes hold of that seed field and goes to work on it. The sun's rotation, which is faster at the equator than at the poles, grabs the field lines and stretches them, winding them around the star like thread around a spool, amplifying and tangling them, concentrating them into intense magnetic knots. Those knots eventually become buoyant and burst up through the surface, and where they emerge, they form sunspots, the dark blemishes that multiply as the cycle builds. And sunspots are the arsenals of the sun. Their twisted, stressed magnetic fields store colossal energy, and when those fields snap and reconnect, the energy is released as solar flares, the most powerful explosions in the solar system, and as coronal mass ejections, billion-ton clouds of magnetized plasma hurled into space. Seed, dynamo, sunspots, storms. The fury that erupts from the sun's middle latitudes is grown, cycle after cycle, from the field that was gathered at its poles. This is why the strength of the polar field predicts the violence of the next cycle better than anything else we have ever found. A strong seed grows a fierce crop of sunspots and storms. A weak seed grows a milder one. It is also why the reversal we photographed matters so much. The chaotic dissolution and rebuilding of the polar caps at solar maximum is the moment the next seed begins to form. The patches migrating and battling across that messy polar map are, quite literally, the raw material of the storms of the 2030s being assembled in front of our instruments. When you look at the mess in those images, you are not looking at abstract turbulence. You are looking at the early ingredients of future eruptions, future geomagnetic storms, future emergencies at power companies and satellite operators, gathering at the bottom of the sun a decade before they strike. And that reframes everything about why seeing the pole matters. The pole is where the sun's future violence is written first. Every question that keeps space weather forecasters awake: how strong will the next cycle be? When will the fury peak? Is a question about the polar field. For all of history, we tried to read that field edge-on, through a distorting angle, and our forecasts have been rough guesses as a result. Now at last, a spacecraft can read the seed directly. But before we celebrate that progress, you need to understand what is actually at stake when the seed grows. Because we have been speaking of solar storms in the abstract, as a danger looming behind the science. It is time to make that danger concrete. The sun has already shown us, more than once, exactly what its storms can do to the world of human beings. And the first time it showed us, it set the sky on fire from pole to pole and turned the most advanced technology of the age against its own operators. To understand what the sun's storm engine can actually do, we go back to the 1st of September, 1859. On that day, a British astronomer named Richard Carrington was doing what he did every clear morning, projecting an image of the sun through his telescope and carefully sketching the sunspots on its face. He was studying an enormous, complex group of spots, one of those magnetic arsenals we just described, when something happened that no scientist had ever recorded. 2 points of blinding white light erupted within the sunspot group, brightening and blazing for about 5 minutes before fading away. Carrington had just witnessed, live, a solar flare, the snap and explosive release of a stressed magnetic field. He was watching the sun's storm engine fire, and he had no idea what was about to follow. What followed was the arrival, less than a day later, of the storm itself. The flare had been accompanied by a colossal coronal mass ejection, a billion-ton cloud of magnetized plasma blasted directly at the Earth, and it crossed the 93 million miles between us with unusual speed, likely because an earlier eruption had swept the path clear. When it slammed into the Earth's magnetic field, it triggered the most intense geomagnetic storm in recorded history, an event we now call the Carrington event. The Earth's magnetic field convulsed, and the world, the pre-electric world of 1859, experienced something biblical. Auroras, the polar lights normally confined to the far north and south, exploded across the entire sky, seen from the tropics, from the Caribbean, from latitudes where no living person had ever seen them. The displays were so brilliant that people could read newspapers by their light at midnight. In some places, birds began singing and workers rose and started their day, believing dawn had come. Others saw the blood-red glow on the horizon and feared distant cities were burning. For 2 nights, the sky of planet Earth was on fire. But the truly prophetic part of the Carrington event was what it did to technology. In 1859, humanity possessed exactly one electrical network, the telegraph, a simple web of wires strung between cities, and the storm seized it. The convulsing magnetic field of the Earth induced surging electrical currents in those long wires, exactly the phenomenon we now call geomagnetically induced currents. Telegraph systems across Europe and North America failed spectacularly. Operators were struck by electric shocks from their own equipment. Sparks leaped from the instruments. In some offices, the surging current set the telegraph paper on fire. And in the storm's most famous demonstration, some operators discovered they could disconnect their batteries entirely and keep sending messages using nothing but the current the storm itself was driving through the wires. The sun was powering the telegraph network. Humanity's first electrical technology had been turned into a passive antenna for a solar storm, and it had buckled. Now hold that image and consider what it means. The Carrington event struck a world with almost nothing electrical to destroy, and it still set fires, injured operators, and seized the one network that existed. Our world is that world's opposite. We have wrapped the entire planet in exactly the kind of long conductive wiring that the storm attacked, power grids spanning continents, and we have made everything, water, food, finance, communication, medicine, dependent on it. Scientists who study the Carrington event estimate that a storm of that magnitude striking today would induce those same surging currents in our power grids on a continental scale, with the potential to damage the great transformers that grids depend on, machines that take months or years to replace. The most powerful storm in recorded history is not a quaint historical episode. It is the benchmark, the demonstrated capability of our star. Unless you think such storms belong safely to a distant century, the sun has provided far more recent reminders. Because within living memory, a far weaker storm than Carrington reached down and switched off the power for millions of people in 90 seconds. March 13, 1989. In the early hours of the morning, the province of Quebec in Canada was asleep, its cities glowing, its power grid humming, carrying electricity to millions of people across a vast, frozen territory. Days earlier, the sun had erupted, hurling a coronal mass ejection toward the Earth, and that night the cloud arrived, slamming into our planet's magnetic field and setting off a powerful geomagnetic storm. Auroras flared across the sky, seen far south of their usual haunts, and in the wires of Quebec's power grid, the storm began to induce currents, rogue electricity flowing where it was never meant to flow, driven by the convulsions of the Earth's magnetic field. What happened next unfolded with terrifying speed. The induced currents surged through the grid, saturating and stressing its equipment, and protective systems began tripping in a cascade, each failure loading more strain onto what remained. From the first sign of trouble to total collapse took less than 2 minutes. In roughly 90 seconds, the entire Quebec power grid failed, and 6 million people were plunged into darkness in the middle of a freezing March night. The blackout lasted around 9 hours. Schools and businesses closed. The subway in Montreal stopped. Airports struggled. Families woke to cold, dark homes with no idea that the cause of their blackout was an explosion on a star 93 million miles away, days earlier. A cloud of solar plasma had crossed interplanetary space, shaken the Earth's magnetic field, and switched off a modern power grid the size of a country in the time it takes to brush your teeth. The Quebec blackout deserves its place in this story because of what it proved. This was not the 19th century telegraph age. This was a modern, industrial power system, engineered with safeguards, and a solar storm collapsed it in seconds. And here is the crucial detail. The '89 storm, powerful as it was far weaker than the Carrington event. It was a serious storm, not a historic monster, and it still blacked out millions and came close to cascading into neighboring grids in the United States. Engineers studying the event realized how narrow the margin had been, and utilities around the world began, for the first time, to take space weather seriously as a threat to infrastructure. The sun had demonstrated, on a modern grid, exactly the failure mode that scientists fear on a continental scale from a Carrington-class event. Quebec was the small dress rehearsal, and the reminders have continued into our own decade. In May of 2024, a barrage of eruptions from a single enormous sunspot group struck the Earth one after another, merging into the strongest geomagnetic storm in more than 20 years, an event powerful enough to push auroras to latitudes where millions of people saw them for the first time in their lives. That storm disrupted satellites, degraded precision navigation systems that industries like farming depend on, and forced grid operators into protective measures. Though the world escaped serious damage, it was beautiful, and it was a warning. The machinery that produced Carrington and Quebec is not retired. It is running right now, at the height of the current cycle, the same cycle whose flipping engine solar orbiter photographed at the pole. The storms are not history, they are weather, and the most frightening demonstration of that came just over a decade ago when the sun fired a shot of full Carrington scale, and the only thing that saved our civilization was a coincidence of timing. Of everything in this story, the event we describe now may be the one that should genuinely keep you up at night. It is not famous. There was no blackout, no burning sky over the cities of the world, no disaster reported on the evening news. And that is precisely the point. In July of 2012, the sun unleashed a storm comparable to the Carrington event, a full-scale, civilization-threatening monster. It crossed the orbit of the Earth, and it missed us not because it was weak, and not because we were protected, but because of timing. 9 days of timing. Here is what happened. On the 23rd of July, 2012, an active region on the sun erupted with staggering violence, launching one of the fastest and most powerful coronal mass ejections ever recorded, a cloud of magnetized plasma comparable to the one that caused the Carrington event, tearing through space at extreme speed. The eruption was aimed squarely at the Earth's orbit, at the precise track our planet follows around the sun, and it hit that track. The storm swept directly through the region of space where the Earth travels. But the Earth was not there. Our planet, moving along its orbit, had passed through that exact location roughly 9 days earlier. The storm crossed our path behind us, like a truck barreling through an intersection moments after you have driven through it. Had the eruption occurred about a week and a half sooner, the Earth would have been standing directly in its path, and the full force of a Carrington-class storm would have struck our modern, electrified, satellite-dependent world head-on. We know how serious it was because the storm did not vanish into empty space unobserved. By pure good fortune, a solar-observing spacecraft was positioned in the storm's path, and it flew through the event, measuring it from inside. The data confirmed the researchers' fears. This was the real thing, a storm of historic magnitude, fully capable of Carrington-scale effects at the Earth. Scientists who analyzed it afterward delivered assessments that are chilling in their bluntness. If it had hit us, one leading researcher said, we would still be picking up the pieces years later. Studies of such a direct hit projected damage to power grids, satellites, and infrastructure running into trillions of dollars, with recovery times measured not in days but in months and years, blackouts of unprecedented scale and duration, cascading failures through water systems, supply chains, finance, and communication. The disaster that defines the space weather nightmare scenario was launched, at full power at our orbit, within the lifetime of almost everyone watching this. And the margin by which it missed was 9 days of orbital timing. Sit with that for a moment because it reframes the entire subject. We tend to file catastrophic solar storms in the same mental drawer as asteroid impacts, real in principle, comfortably improbable in practice. The 2012 event says otherwise. The sun demonstrably fires Carrington-class storms in our era, at our orbit. One of them has already crossed our path in this century. The question of whether such a storm will one day strike the Earth is not really a question of if. Across enough time, with the sun erupting cycle after cycle, it is a question of when, and of whether we will see it coming with enough warning to protect what can be protected. Which returns us, with new urgency, to the pole of the sun. Because every hope we have of anticipating the sun's fury, of knowing how violent the coming cycles will be, runs through that chaotic region solar orbiter photographed. And one of the first things the spacecraft did after taking the pole's portrait was to begin watching the machinery there in motion. What it measured was our next surprise. To understand the next discovery from the pole, you need to meet one of the most majestic pieces of machinery inside our star, a slow, planet-spanning circulation of plasma that scientists often describe as the sun's conveyor belt. It is one of the key mechanisms that builds the polar field, the storm seed we have been tracking all night. And with Solar Orbiter finally positioned above the pole, humanity gained its first chance to watch the end of that conveyor belt, the place where it delivers its cargo directly. What the spacecraft found there did not match the expectations. Here is the machinery. Beneath and across the sun's surface in each hemisphere, an enormous, slow circulation of plasma is constantly turning. Near the surface, the flow moves from the equator toward the pole, a vast, gentle current carrying material poleward across the face of the star. Deep in the interior, the flow returns, traveling from the poles back toward the equator, completing a great loop, one colossal circulation cell in the north and its mirror in the south. This is the meridional flow, the conveyor belt, and it turns with extraordinary slowness, taking years, more than a decade, to carry material through a single loop. Its speed at the surface is astonishingly gentle for an object as violent as the sun, a drift of mere meters per second, walking pace, on a star where other flows rage at hundreds of kilometers per second. And yet this gentle drift is one of the most consequential motions on the Sun. Because the conveyor belt carries the magnetic field. Remember that the Sun's plasma and its magnetic field are locked together, the field dragged wherever the plasma flows. So as the surface conveyor drifts poleward, it sweeps magnetic fragments along with it, carrying the debris of decayed sunspots, patches of magnetic field from the active latitudes, slowly and steadily toward the poles. This is how the polar cap is built. The new polar field, the seed of the next cycle, is assembled piece by piece from magnetic fragments delivered by the conveyor belt, accumulating at the pole over years until a coherent cap of new polarity takes hold. The chaotic patchwork solar orbiter photographed, the battlefield of old and new polarities, is precisely this delivery process caught mid-operation, fresh fragments of the new polarity arriving on the conveyor and fighting for territory against the crumbling remains of the old cap. The mess at the pole is the conveyor belt's loading dock during its busiest season, and this makes the speed of the conveyor belt one of the most important numbers in solar physics. How fast the belt runs helps set the rhythm of the entire cycle and the strength of the seed it assembles. Run the belt faster or slower in the models, and the character of the coming cycles changes. For decades, scientists could only estimate the belt's polar speed indirectly, from the ecliptic, squinting edge on at flows near the pole, with all the distortion that viewpoint imposes. Nobody had ever measured the conveyor belt at its destination, at the pole itself, watching the magnetic cargo actually arrive. That changed with Solar Orbiter's climb. In observations analyzed and announced in late 2025, scientists used the spacecraft's polar vantage to track, for the first time, the magnetic field in motion at high solar latitudes, timing the poleward drift of the magnetic fragments directly. It was a first in the history of solar science, the conveyor belt of the Sun, clocked at the pole. And the reading on the clock was not what the models had predicted. When the scientists analyzed Solar Orbiter's tracking of the magnetic field near the South Pole, measuring how quickly the magnetic fragments were drifting poleward, the number that emerged carried a surprise. The field was migrating toward the pole at a drift of roughly 10 to 20 meters per second, a gentle walking pace by human standards. But the surprise was not the gentleness. The surprise was that this was faster than expected. The magnetic field at high latitudes was being carried toward the pole more quickly than the models had anticipated, and the flow up there resembled the brisker transport seen at lower latitudes rather than the sluggish creep the theories had assumed for the polar approach. The conveyor belt at its destination was running ahead of schedule. Now, a drift of meters per second on an object the size of the Sun may sound like a trivial detail, the kind of decimal point correction that only specialists could care about. It is anything but. Recall what this particular flow does. It delivers the seed. The rate at which magnetic fragments are transported to the pole helps determine how quickly the new polar cap assembles, how strong that cap becomes, and through the cap, how fierce the following cycle will be. The conveyor belt's speed is wired directly into the machinery that sets the amplitude of future solar fury. A belt running faster than the models assume means the models are mistiming and potentially misweighing the assembly of the very field they use to forecast the coming storms. Every cycle prediction scheme that leans on polar field buildup inherits an error from a mismeasured belt. In the business of forecasting a star, this is not a decimal point. It is a gear in the engine, measured for the first time and found to be turning at the wrong speed relative to the blueprints. And there is a deeper significance here, one that echoes through the entire history of science. This is what happens reliably when humanity observes a place directly for the first time. The general picture survives. The theories predicted a messy flipping pole and a poleward conveyor, and both are real, but the specifics come back wrong. The belt is faster than drawn. The details deviate from the blueprint. Before March of 2025, every number describing the sun's polar flows was an extrapolation, an inference made from the wrong angle, and this first direct measurement immediately caught one of those numbers out. It will not be the last. The honest lesson of the faster-than-expected flow is that our quantitative picture of the sun's storm engine, the picture underlying every forecast of every coming cycle, has been built on unverified assumptions about a region we had never seen, and the very first verification found a discrepancy. For the scientists, this is not a defeat. It is exactly the treasure they climbed out of the ecliptic to find. A measured discrepancy is a correction you can feed back into the models, a recalibration of the engine's blueprints using the engine's real behavior. In the years ahead, as Solar Orbiter watches the belt deliver its cargo season after season, the models of the solar cycle will be rebuilt around real polar data for the first time, and the forecasts that depend on them should, gradually, become something they have never truly been: trustworthy. But that word, forecasts, brings us to the most uncomfortable stretch of this entire story, because we have been circling a fact all night, and it is time to face it directly. Humanity, for all its telescopes and spacecraft and models, cannot predict its own star. And the record of our attempts is genuinely humbling. There is one more finding from these first polar campaigns that deserves its own moment, because it adds a strange and consequential wrinkle to everything we have described. The sun, it turns out, does not treat its two poles equally. When Solar Orbiter's instruments measured the magnetic field at the South Pole, and then, in a separate campaign about a month later, at the North Pole, the two measurements did not mirror each other. The magnetic flux, the amount and distribution of magnetic field across each polar cap, showed a different pattern in the south than in the north. The two ends of our star, which the tidy textbook picture draws as perfect mirror images, are not behaving like mirror images at all. The sun's poles are out of step with each other. At first hearing, this might sound like a minor footnote. It is anything but, and solar scientists have suspected something like it for a long time from their distorted edge on glimpses. The two hemispheres of the sun often march through the cycle slightly out of sync. One hemisphere's activity can peak before the others. One pole can complete its magnetic reversal months, even a year or more, ahead of its twin, leaving the sun, for a stretch of time, in a genuinely bizarre configuration, a star whose two poles briefly share the same magnetic polarity, or where one pole has finished flipping while the other still churns in chaos. The fresh polar measurements, showing the two caps with visibly different magnetic distributions, are the most direct look ever taken at this lopsidedness, caught right in the middle of the current reversal. The battlefield at the South Pole and the battlefield at the North Pole are not fighting the same battle on the same schedule. Why does this asymmetry matter to anyone beyond specialists? Because the seed of the next cycle is not one field but two, one cap at each pole, and the coming cycle grows out of both. If the two poles rebuild at different speeds and to different strengths, the next cycle inherits that imbalance, with one solar hemisphere potentially running hotter than the other, producing more sunspots, more eruptions, more of the storms that concern us from one half of the star than from the other. Hemispheric asymmetry feeds directly into the difficulty of prediction. It is one more moving part, one more way the engine can deviate from the simple models, one more reason the forecasts stumble. A star with two mismatched seeds is harder to predict than a star with one, and ours, the new measurements confirm, is a star with two mismatched seeds. The gauge we have finally learned to see is not a single dial. It is a pair of dials, and they do not agree. And there is something almost eerie in this picture, worth pausing on before we move to the forecast problem itself. We are accustomed to thinking of the sun as a single, unified thing, one star, one behavior, one temper. The polar measurements reveal something more unsettling, a star whose two halves are, in a magnetic sense, slightly different creatures, cycling through their transformations on their own offset schedules, joined at the equator into one blazing whole. The chaos at the bottom of the sun is not even the same chaos as the chaos at the top. Both must be watched. Both must be measured, cycle after cycle, if the forecasts are ever to be trusted. Which is precisely why the mission's continuing climb matters so much. Every future pass will image both poles, again and again, building the first true history of both dials of the gauge. But before that future arrives, we must confront the uncomfortable present, the state of solar forecasting as it stands today. Because the record of humanity's attempts to predict this two-faced star is, to put it gently, humbling. Here is the confession at the heart of modern solar science, the fact that gives this entire night its edge. We cannot reliably predict the sun, not its next great storm, and not even the general fury of its next cycle. The most consequential star in our lives, the one whose eruptions can reach into our grids and satellites, operates on a schedule we have never successfully mastered. And this is not for lack of trying. Predicting the solar cycle is one of the oldest continuous forecasting efforts in science, and its track record is a lesson in humility. Consider what prediction would mean and why it is so hard. The solar cycle is famously called an 11-year rhythm, but the sun honors that number loosely. Real cycles have run short and long, stretching and shrinking by years. Their strength varies wildly. Some cycles crowd the sun with sunspots and hurl storm after storm. Others pass weakly, and the sun has even fallen, historically, into decades-long slumps of barely any activity at all. The engine behind all this, the dynamo, is a churning, turbulent, nonlinear machine buried beneath the surface of a star, and turbulence resists forecasting by its very nature. Before each new cycle begins, panels of the world's leading solar physicists convene to issue an official prediction of the coming cycle's strength and timing, weighing dozens of competing methods. And those official forecasts have repeatedly been wrong. The current cycle is the freshest example. It was forecast to be weak, similar to its mild predecessor. Instead, it surged past the predictions, arriving earlier and far stronger than the official consensus expected, producing in a single recent year more powerful eruptions than any year in decades. The experts convened, deliberated, published, and the sun disregarded them. Now connect this to everything we have seen tonight. The best single predictor humanity has ever found for a coming cycle is the strength of the polar field, the storm seed at the poles. And for the entire history of the forecasting effort, that predictor has been measured through the distorting squint of the ecliptic, edge-on, degraded, uncertain. Our most reliable gauge of future solar fury has been read always through frosted glass. Is it any wonder the forecasts stumble? This is the deeper meaning of solar orbiter's climb, and the honest resolution of the paradox we raised earlier. The models correctly predicted the qualitative chaos of a flipping pole, yes. But the quantitative forecast, the one that tells power companies and satellite operators what is coming, has never been trustworthy, and its weakest link has always been our blindness to the poles. We have been trying to predict the output of an engine while unable to see its fuel gauge. And that is the fear worth carrying out of this story, stated plainly. It is not that the pole looked chaotic. It is that we live permanently at close range to a star whose violence arrives on a schedule we cannot read, whose greatest recorded storm required no exceptional cycle to produce, and whose next monster could be assembling in this cycle or the next, unannounced. The Carrington event itself did not strike during some legendary supercycle. It erupted from a star behaving within its ordinary range, a reminder that catastrophic storms do not politely wait for the cycles we would flag as dangerous. Unpredictability is not a gap in our knowledge of the threat. It is the threat. And it is against exactly this that the view from above the pole matters most. Because the pole is where the fuel gauge lives, and for the first time we can finally see it. What, then, does the gauge currently read? That is our next stop, and the reading is strange enough to deserve its own chapter. So what does the newly visible fuel gauge of the sun actually read, right now? As the reversal grinds on and the new polar caps begin to assemble out of the chaos, scientists have been watching the buildup of the new polar field with intense interest, because this emerging field is the seed of the next cycle, the one that will govern the sun's fury through the 2030s. And the early readings have raised eyebrows across the field of solar physics. The new polar field appears to be coming in unusually weak. Assessments published as the buildup proceeded have indicated that the polar field is at a strikingly low level compared to the equivalent stage of the last several cycles, one of the weakest polar field readings in decades of measurement. Taken at face value, through the standard logic of the seed, a weak polar field points toward a weaker next cycle. Fewer sunspots, fewer eruptions, a milder solar decade ahead. And scientists have been careful to attach the honest caveats. The buildup is still in progress. The field could strengthen substantially in the coming years before the next minimum locks in the seed. And the newly discovered quirks of the polar machinery, like that faster-than-expected conveyor, mean the very rules for reading the gauge are being rewritten even as we read it. The weak reading is a genuine, intriguing signal, not a settled verdict, but suppose it holds. Suppose the next cycle really does arrive feeble, the sun subdued, its face quieter than it has been in generations. Here is the question that matters. Would that actually make us safe? And the answer, delivered by the sun's own history, is unsettling. No, a quiet cycle is not a safe cycle. We have already seen the proof tonight, hiding in plain sight. The Carrington event, the most powerful storm in recorded history, did not erupt from some monstrous, hyperactive cycle. It came from a sun operating within its ordinary range, in a cycle that history does not remember as exceptional. Powerful eruptions require a single sufficiently violent active region, one large, twisted sunspot group with enough stored magnetic energy, and such regions can and do appear even when the cycle as a whole is modest. A weaker cycle shifts the odds. Fewer arsenals on the surface means fewer chances for a monster, but it does not disarm the star. The sun can throw a historic storm from a mediocre cycle the way a quiet year of weather can still produce a single catastrophic hurricane. The gauge may promise a calmer decade on average, and the average may arrive exactly as promised, right up until the one afternoon it doesn't. There is also a subtler trap hidden inside a quiet sun, and it is a human one. Calm breeds complacency. A weak cycle means years with few storms, years in which space weather fades from headlines, budgets, and priorities, years in which our civilization grows even more dependent on satellites and grids while the memory of the threat evaporates. And all the while, the exposure grows. Every year we add more satellites, more electrified infrastructure, more digital dependency, so that the same storm does more damage striking us later than it would striking us now. A long, quiet spell followed by one bad day is, in some ways, the most dangerous sequence the sun could deal us. So the strange, weak reading at the poles is not a lullaby. It is simply the first honest look at a gauge we have never before been able to see, on an engine that has surprised us before and will surprise us again. Which raises the final practical question of the night. Given a star we cannot predict and cannot pacify, what do we actually do? The answer is the reason missions like this one exist at all. Let's be clear about what we can and cannot do about the sun. We cannot stop a solar storm. We cannot shield the entire planet, and we cannot reach into the dynamo and comet. The star will erupt when it erupts. But helplessness is not the end of this story, because there is an enormous difference between a storm that arrives unannounced and a storm we see coming. Almost everything that makes a great solar storm catastrophic can be reduced, sometimes dramatically, with warning time and preparation. And that is what the view from above the pole is really for. It is how fear gets converted into foresight. Consider what warning time buys. A coronal mass ejection, the billion-ton cloud that does the real damage, takes 1 to 3 days to cross from the sun to the Earth. That is the window. With good monitoring, we see the eruption launch, we track the cloud, and in those hours before impact, the vulnerable systems of civilization can brace. Power grid operators can reduce loads, reconfigure their networks, and protect the great transformers whose destruction would turn a blackout of hours into a blackout of months. Satellite operators can place their spacecraft into safe modes. Airlines can reroute polar flights. Astronauts can take shelter. None of this prevents the storm, but together it can be the difference between a hard week and a crippled decade. Forewarned in space weather genuinely is forearmed. And the quality of all of it, the forecasts of the cycle years ahead and the warnings of the storm days ahead, rests on how well we understand the engine, which is exactly what the polar observations are transforming. Everything Solar Orbiter is doing above the pole feeds this machinery of foresight. Direct measurements of the polar field replace the frosted glass readings that cycle forecasts have always leaned on. The clocked conveyor belt corrects the gears inside the prediction models. Watching the reversal complete, watching the new caps assemble in real time, gives forecasters their first ever ground truth view of the seed as it forms. And the mission is only getting started. Solar Orbiter's stairway has more steps. In the years ahead, further Venus flybys will tilt its orbit steeper still, lifting it beyond 20 degrees and eventually past 30 degrees above the solar equator, each climb delivering a more direct, less distorted view of the poles than the one before. The images from March of 2025, historic as they are the worst polar views the mission will ever have. Everything from here improves. The mission's own scientists have said it plainly. These first images are just the first step, and the data to come will transform our understanding of the sun's magnetic field, its wind, and its activity. So this is the sober, unsensational answer to the fear this story raises. We live beside a star we cannot predict, whose storms have already burned telegraph wires, darkened provinces, and missed our modern world by 9 days. And our response, the only response available to a species in our position, is to watch it better than it has ever been watched. To climb out of the plane, stare down at the control room, measure the seed, clock the machinery, rebuild the models, and stretch every hour of warning we can out of the physics. The terrifying thing about the pole is what it governs. The hopeful thing about the pole is that we can finally see it. And that trade dread exchanged for vigilance is the oldest bargain in the human story. Which brings us to the last reflection of the night, the strange, permanent condition that all of this reveals. what it actually means to live forever beside a star like ours. Step back now and take in the full picture this journey has revealed, because it describes not an event but a condition, the permanent situation of our species. We live at close range to a star. Not a metaphorical fire in the sky, but a genuine star, a churning sphere of plasma 1,000,000 times the volume of our planet, wrapped in a magnetic field that it demolishes and rebuilds in an eternal cycle, capable of explosions carrying the energy of billions of nuclear weapons, and near enough that its eruptions cross to our doorstep in a day or three. Everything we love, everything we have built, sits 93 million miles from that engine. That is not a crisis. It is simply the address of the human race. And what the events of 2025 added to that picture is the intimate, unsettling detail. We have now seen the engine's control room, and we found it in upheaval, a pole dissolved into warring polarities, a star caught in the act of turning its own magnetism inside out. We learned that this upheaval is not an anomaly, but the sun's routine, performed every 11 years since before there was life on the Earth to notice. We learned that the machinery assembling the next round of fury runs faster than our blueprints claimed. We learned that the gauge which foretells the coming decade is reading strangely low, and that even a low reading is no promise of safety, because the greatest storm in our records needed no great cycle to produce it. And beneath all of it, we confirm the oldest, humblest truth in solar science. We cannot predict this star. Its rhythms drift, its forecasts fail, its monsters arrive without appointment. The sun is not hostile. It is worse than hostile in a way. It is indifferent, and it is unpredictable, and it is very, very close. But here is the reframing that this whole story earns, and it matters. The unpredictability of the sun is not new. It has been true for the entire history of our species. What is new is that we know it. Our ancestors lived beside exactly this star, through Carrington-class storms and worse, through the great tempests that ancient tree rings and ice cores still remember, and they never knew the danger existed. They could not see the sunspots, could not imagine the flares, had no warning and no understanding when the sky caught fire. We are the first generation of humans who can see the threat clearly, name its mechanisms, photograph its control room, and act on what we learn. Knowledge of a danger, vulnerability. The blindness was the vulnerability. The fear is what progress feels like from the inside. So when you hear that what a spacecraft saw at the sun's south pole is terrifying, understand the statement completely. Yes, the pole is in chaos. Yes, the chaos is the engine of storms that could genuinely wound our civilization. Yes, the engine defies prediction and could already be assembling. All of that is true, and none piece of it was equally true last century, and the century before, when no one knew and nothing could be done. What has changed is us. A species that once worshipped this star without understanding it has climbed above the plane of its own solar system to stare down at the star's hidden machinery, and has begun, for the first time, to read it. The pole of the sun is terrifying in the way that all great truths about our situation are terrifying, right up until they become the tools of our survival. And that transformation from terror to instrument is now underway, 17 degrees above the ecliptic, aboard a small spacecraft climbing higher every year. So the next time you glance at the sun, that steady, dependable disk that has ruled every day of your life, carry with you what you now know about its hidden south pole. Down there, at the bottom of our star, in a region of 2025, the sun's magnetic field is a battlefield. Patches old magnetic identity dissolving, a new one fighting to be born, a star calmly turning itself inside out while lighting your afternoon. The steadiness you see is real, and so is the upheaval you cannot see. Both are the sun. They always have been. We began tonight with a promise that what was found at the pole should genuinely unsettle you, and by now you understand exactly why, and exactly how honestly that claim holds. Not because the chaos surprised the scientists, it did not. Their models predicted a flipping pole would look like a mess, and the mess arrived on schedule. The unease lives deeper. It lives in what that pole governs. The chaos we photographed is the workshop where the sun's next decade of violence is being assembled, the seed of the cycle that will hurl the flares and the billion-ton clouds of the 2030s. It lives in the record of what those storms have already done, the burning telegraphs of 1859, the 90-second collapse of a modern grid, the Carrington-class monster that crossed our orbit 9 days behind us. And it lives, above all, in the confession at the heart of solar science, that this engine has never yet been predicted successfully, that its gauges have only just come into view, and that its greatest storms do not wait for the cycles we would think to fear. But let the story end where it truly ends, not in dread but in the remarkable fact of the seeing itself. For the entire existence of our species, the poles of the sun were invisible, and the storm engine of our star did its work in perfect secrecy. That secrecy is now over. A spacecraft built by human beings, flung around Venus again and again, climbed out of the plane of the planets and looked down into the control room, and humanity watched a star mid-transformation for the first time. The conveyor belts are being clocked. The seed is being weighed. The models are being rebuilt around truth instead of guesswork. Every year from now on, the view improves, the blind spot shrinks, and the warning we might one day desperately need grows a little more possible. The chaos at the bottom of the sun has been there, cycle after cycle, for 4.5. What is new? Finally saw it. So look up carefully at that ancient and unpredictable star, and hold both truths at once. And every living thing you have ever known. And it is a restless magnetic engine, flipping and storming on a schedule no one can read, with a battlefield hidden at its bottom and a history of reaching across 93 million miles to touch the works of human hands. Respect it. Watch it. Support the watchers and never mistake its steadiness for stillness. Because the sun has never turmoil until now. And now that we have seen it, now that the last hidden place on our star has finally shown us its chaos, we are, for the first time in the long history of our species, no longer entirely in the dark beneath our own sun.